Good evening, everyone. I'm going to be presenting our paper, Design and Analysis of Flexible Joints for a Robust 3D Printed Prosthetic Hand. Here are our names and our contact information. Here's our agenda. We're going to be talking about our context and motivation, our objectives, the flexible joints for a robust 3D printed prosthetic hand, our implementation and results, and finally, we're going to be talking about our conclusions and future works. So, for context, body-powered upper limb prosthetics are driven by non-elastic cables for the flexion movements and elastic cables or flexible joints for the extension movement. These upper limb prosthetics can be classified based on the level of amputation. For example, partial hand amputation requires prostheses for the hand, which are actuated by the wrist. Wrist disarticulation and below elbow amputation requires prostheses for the hand and wrist, which are actuated by the elbow. Above elbow amputation requires prostheses for the hand, wrist, and elbow that will be actuated by the shoulder. And finally, in shoulder disarticulation, the body-powered prostheses cannot be used. There's a rising need for low-cost, low-maintenance prostheses, and developments in 3D printing hand designs can satisfy those basic requirements with affordable and lightweight alternatives. Most of the available 3D printed prosthetic hands are controlled by the wrist because 65% of individuals with missing limbs have transradial amputation. The body-powered, wrist-controlled prosthetic hands are light and low cost because there are no controllers or electrical devices needed for the hand actuation. Our motivation for this work is based on the fact that around 3 million persons worldwide have upper limb amputation, and 80% of these individuals live in resource-constrained countries. In addition to that, in the recent global conflicts, the Syrian war left 80,000 wounded individuals, with hundreds of them needing prosthetic limbs. The problem right now is that there could be several possible sources of failure in this new generation of prosthetic hands. The cables can break or the plastic can be damaged. Failure of the finger joints can occur when the prosthetic hand is pressed on a flat surface, and there can also be an overextension of the joints in instances like pushing a door. We design flexible joints from elastomeric materials instead of plastic joints so that we can make the current 3D printed prosthesis designs more robust. Our work has implications in the design of 3D printed prosthetic hands that can be deployed for war-wounded refugees or for those in low-resource countries. Objectives. In our work, we investigate the flexibility of different designs of the soft joints of a low-cost 3D printed prosthetic hand with respect to material type. We present a possible solution to the component that can cause failures as described in the previous section, and we try to replicate the human hand's natural pose by replicating the joint angles in the prosthetic hand. For the mechanical design and mechanism, we analyzed the Flexi hand, which is a representative of openly accessible 3D printed hands. This body-powered hand is wrist-controlled and uses non-elastic cables for flexion movement for grasping or holding objects. To open the hand and release the objects, the flexible joints are used for the extension movement through the structural elastic deflection. Here you can see an image of the Flexi hand. For the kinematics analysis, forward kinematics was carried out to determine the final position of the hand's fingertip. We used and considered Denevitt-Hardenberg parameters, and the Denevitt-Hardenberg technique is an approach used to create the transformation matrices based on 4 parameters determined from the link frame of a robotic system. In here, you can see the variable assignments for links and joints of the finger in this table. So the final X and Y positions of the fingertip can be calculated from these 2 equations. The extension movement of the prosthetic hand is actuated by flexible joints, where each joint has 1 degree of freedom. They can be considered as critical parts of the design because of the cyclic bending. Numerical study was carried out to evaluate the behavior of the flexible joints and to improve its lifetime. 2 design parameters were studied: the joint geometry and the material type. Here you can see that we included 3 geometries that can be easily constructed. The design of the first one was the joint that was originally created by the Flexi hand designer. The second was inspired from the first one, but we tried to use less material in its middle part because of cost purposes. And finally, the third one was developed to give more flexibility in the joint itself. We also used two materials, polyurethane and silicone, and in this table you can see the mechanical properties of each of them. Here's our case study. We use this software for the nonlinear analysis. Now, we use nonlinear modeling because it's recommended for the formable material, and silicon and polyurethane behave nonlinearly after exceeding their elastic limits. We didn't consider damage theory because the applied force is relatively small, so no significant deformation was going to be observed, and we also neglected the effect of torsion. It was modeled that one side of the joints is fixed, while the other is under the effect of loading. We subjected the different designs to a load at one end with 5 newtons distributed load, and we collected the results after 0.35 seconds. As part of this case study, we also wanted to compare the calibrated prosthetic hand joint angle with the human hand's natural pose. So, to collect the data, 4 volunteers participated in an experimental measurement of their hands. Here are our results. For the design 1, we can see that we found that stress concentration region was located at the fixed edge of the design, and the maximum stresses obtained were 0.189 and 0.143 megapascals for polyurethane and silicon respectively. For design number 2, the fixed end experienced some deformation with high stress concentration. The maximum stresses obtained were 0.233 and 0.276 megapascals, again with polyurethane and silicon respectively. And in design number 3, we found that the weak points are the locations with less thickness. Once again, the maximum stresses obtained were 0.185 and 0.399 megapascals for polyurethane and silicon respectively. So, in general results, polyurethane showed more flexibility than silicon under 5 newtons of loading. And design number 2 showed more flexibility than design number 1, but stress concentrations were higher. Design number 3 showed good flexibility, but had high stresses in the corners. Here you can see design number 1, design number 2, and design number 3 with polyurethane on the left side and silicon on the right one. Okay, so to validate the kinematic analysis of the middle finger and to test the performance of the flexible joints, the middle finger was subjected to some bending angles, and the final X and Y positions of the fingertip were recorded. The results show that minimal errors occurred due to the finger thickness, which was not considered in our kinematic analysis. Now, the collected joint angle data of the human hand or 4 people that help us with this, they were compared with the calibrated prosthetic hand. We found that MCP prosthetic hand angles were close to the mean values of the human MCP angles, with a difference of around 1 degree. PIP were in the range of 10 degrees difference, while DIP prosthetic hand angles had approximately 2 degrees difference. With these results, it can be shown that obtaining the natural pose can be replicated for MCP and DIP joints. Now, the PIP joint, the difference was greater than the expected because non-elastic cables are not directly connected to this joint. So there was a difference right there. Here you can see the comparison of human and prosthetic fingers, and you can also see the comparison of theoretical and experimental X and Y positions of a male finger with respect to the angles. So, conclusion and future works. We investigated a possible solution to a component that could be a presumable cause of failure so that we can make the current 3D printed prosthesis design more robust. We found that design 1 with a polyurethane material show a good performance in forming a pose similar to the human hand in its natural position. For future works, we found that this work has implications for a more robust design of 3D printed prosthetic hands that can be provided to amputees who may need them immediately. This improvement can make their prosthesis last longer as they wait for better alternatives. Here you can see the comparison that we did from the subject position and the 3D printed hand position. So that concludes our presentation. Thank you so much for your time, and here's our contact information in case you have any further questions or doubts about our project or implementation. We will be gladly attending all of you. Do you have any questions?